So this section will revisit the idea of dummy variables. We'll go into a little bit more detail, and I'll also show you how you can convert qualitative variables to dummy variables in Excel. So we've talked about two different variable types, categorical versus quantitative. Things that are quantitative are measured as a number. There is some quantity. Kids, weight, GPA, income, how old you are, how tall you are. Those are all quantitative variables. Categorical or qualitative variables are exactly what they sound like. They assign an observation to a category and they describe something. So they can describe gender, they can describe your major, they can describe the zip code where you live, they can describe the county. Those are all things that are qualitative, and we are often interested in those types of variables when we're estimating regressions. So, is there a difference in wages for males and females? Is there a difference in average starting salary for econ majors versus non-econ majors? So these are things we are often interested in, but we have to convert these qualitative categorical variables to something that's quantitative so we can include it in the regressions. And we do that using dummy variables. So we convert these words to zeros and ones so that we can include them in a regression equation. And we've already seen some of this. So when we're looking at these sales price regressions, the dependent variable was the sales price of a house, which was quantitative. The size of the house, so square footage and age, these two variables were continuous, but these three variables were categorical. So, does the house have a pool? Yes or no? Does the house have a fireplace? Yes or no? Is the house in a college town? Yes or no? All of these things are included as dummy variables. So if the house has a pool, we convert the yeses to a 1, the no's to a 0, and then we can include that 0, 1 variable in the regression. Same thing is true with fireplace, and same thing is true with college. And we interpret the coefficients on dummy variables in a slightly different way as well. So for this coefficient right here on square foot, we would say, holding the other independent variables constant, if we increase square footage by 1 unit, the sales price increases by $83.18 on average. So it's the change in the average sales price when we change the square footage by 1 unit. So change over change, think of slope. Same thing is true for age. If the home is 1 year older, we increase age by 1 year, the average sales price decreases by $192.99. For these variables that are dummies, it's not the change in sales price if we increase pool by 1 unit, it's the difference in average sales prices for homes with a pool compared to homes without a pool. So if we hold the other variables constant and we have pool versus no pool, the home with a pool would sell for $4,352 more than the home without a pool. And the same thing is true for fireplace in college. It's the sales price when that variable is 1 minus the average sales price when that variable is 0, assuming the other variables are held constant. And these test statistics and p-values tell us whether or not those differences are statistically significant. So we can see for pool it's significant, fireplace is not significant because that p-value is larger than 0.05. This would be at 95% confidence. The p-value on college is 0, which means on average homes in college towns do sell for a statistically significantly higher price that's a statistically higher price than those not in a college town. This next slide has those the interpretation. So you can see the equation, the estimated regression equation written out here, where we're just putting the coefficients for each variable in front of it. So this would be your estimate of B1, B2, B3, B4, and so on. So just notice we interpret the coefficients on dummy variables in a slightly different way. So if a regression only has dummy variables, for example, we just look at the fireplace regression. So we look at homes with a fireplace compared to homes without a fireplace. This just helps you see that the coefficient there is the difference in average sales prices for homes with a fireplace compared to those without. So if fireplace gets set to 0, this entire term goes away. So the expected sales price for a home without a fireplace is coefficient A. For homes with the fireplace, this would be 1. So A plus B times 1 is A plus B. So A plus B is the expected sales price or average sales price for homes with a fireplace. If you take the difference, so if you take A plus B minus A, you're left with B. So that would be the difference in average sales price for homes with a fireplace compared to those without. And now, what we're thinking about with a dummy variable, and one reason I'm covering this again, is we're thinking about um, two different groups. So you have homes with a fireplace, you have homes without a fireplace, and we want to know if those means are statistically different, which should make you think of a t-test. So your brain should be thinking about the t-test that we talked about in the previous sections for independent samples. So if we had a column of data for homes with a fireplace and a column of data for homes without a fireplace, and we do a t-test to see if the means for those two columns are statistically different, you're going to get a p-value. And that's exactly what this p-value is right here. So this p-value right here is exactly the same p-value you should get when you conduct a t-test for the null hypothesis being homes with a fireplace and homes without a fireplace have the same sales price in the population against the alternative that the sales prices are different. Okay. So we have our estimate of the difference, and we have a coefficient that tells us whether or not that difference is statistically significant. So it's basically the same thing. If you have a regression with only a dummy variable, you're basically doing a t-test. The nice thing about a t-test from the regression, again, we have to make this one assumption that the variances are equal. So you would do, I think it's option 2 in Excel instead of the option 3. The nice thing about this is it allows us to control for other variables while comparing the two group means. So you want to think about homes. Let's go back to the franchise and independent real estate example, where we have homes sold by franchise brokers, homes sold by independent brokers. We want to know if the franchise brokers are actually, or if one brokerage firm it does a better job than the other. Well, if the sales prices are different and we reject the null hypothesis that the means are the same, that doesn't necessarily tell us that one firm is better than the other, because it's possible that one firm specializes in home types that are different than the other. So maybe one brokerage type sells newer, larger homes in better school districts. Well, that's going to cause the price to be higher. So in using multiple regression, we can have the sales price as the dependent variable. We can have a dummy variable equal to 1 if the home was sold by a franchised real estate broker, 0 if it's sold by an independent broker, and we can add all of those other characteristics that might explain the difference in sales price. So we can add all the housing characteristics to the regression so that we're holding constant the types of homes they sell in the areas in which they sell homes, and that dummy variable will now tell us if we observe if the difference between the brokerage types, if the sales price between the brokerage types is statistically significant, holding constant the other factors. So if we are statistically controlling for all of the different things that could cause a price to be different, and we still find that one brokerage type does better than the other in terms of sales price, maybe now we can actually say one organizational structure, franchise versus independent, actually performs better than the other one. And that's what we can do with regression. So we can still do this t-test of means, but we can now do this t-test on the means after controlling for all of the other characteristics. Visually, when we're thinking about a dummy variable and what it looks like on the plot, it effectively changes the intercept for the estimated regression line. So depending on the category, you can have an intercept that's higher or lower than the omitted category. So in an example like this, where we have your predicted value, we have an intercept A, B1 times X, where X is continuous. So this is a continuous variable, and this is a dummy variable. We know the slope of the line is going to be b1 because that's the coefficient that's attached to that continuous variable. b2 is attached to a dummy variable. So when d equals 0, the equation of this line is a plus b1x. So that's the equation of the line when d equals 0. But when d equals 1, we get a plus b1x plus b2. So we have two constants floating around, a and b2, because b2 times 1 is just b2. So the intercept when d equals 1 is a plus b2. So the coefficient b2, the coefficient on that dummy variable, is just the difference in the intercepts for the lines when d equals 1 compared to when d equals 0. So it starts at a different point, but the line keeps the same slope. So we can take a look at this regression right here using the same data that we had earlier. If we just run the regression on price plus price as a function of square foot, the slope of the red line that you're seeing here is 86, which says if we increase square footage by 1, the estimated sales price is going to increase by $86. And if you were to run this line all the way back to 0, it would cross the y-axis at $30,920. So that would be the y-intercept or the price intercept when square footage is 0. And we don't care about the that intercept because we don't have any homes in our sample with 0 square footage. But when we add that dummy variable for college, notice we get two estimated lines. So for homes that are not in a college town, so if college equals 0, all of this goes away. So the estimated regression equation the line that we use to make our predictions for homes not in a college town is $5,681 plus 84 times square foot. So that's going to be this line right here. So when college equals 0, we're going to use this line to make our predictions. And the intercept of that line, if you run this all the way back, would be 5,681. That would be the intercept when we assume college equals 0. Now when college equals 1, we get 5,681 plus 84 times square foot plus 60,369 times 1. So our intercept for the college homes would be the 5,681 plus the 60,369. So when we're making predictions for homes in a college town, this line up here is the one that we would be using. And the key thing to take away from this is the difference between this line and this line is exactly 60,369, which tells us if we hold constant square foot, so if we pick a square footage and we compare the college line to the non-college line, the college line will always be $60,369 above the non-college line. So holding constant square footage, the college line is always this much higher than the non-college line. So if we go to 3,000, we compare the lines, the difference is 60,369. If we go down to 2,000, we compare the lines, the difference is 60,369. So that is what a dummy variable does graphically. It changes the intercept. So what if you have more than one category for your dummy variable? Well, you have multiple intercepts. So let's say you have this same type of regression, but you have 3 different neighborhoods. So if you have 3 different neighborhoods, you can put 2 dummy variables in the regression, but your estimated regression line when you plot it would have 3 different intercepts. So you'd have a separate intercept for each of those 3 categories, where the intercept would capture where the intercept here would be the intercept for the group that's omitted from the actual regression equation. So there's a lot more to dummy variables than we covered in that first set of slides, but just this should help you understand exactly what those dummy variables are doing. In the next video, I will show you how to convert qualitative variables in Excel to zeros and ones so that they can be included in a regression.